Right, so we are recording. So we left off on, we are continuing chapter 17. We left off on slide 32, so we're going to continue on to slide 33. And we're talking about, aromatic, non-aromatic, and anti-aromatic. So it says consider a 7-membered ring. So with 6 pi electrons, what they're talking about is this compound right here. They're talking about this right here. So if we think about this, okay, we have a 7-ring compound. If we put all our electrons here, so there's 3 bonding molecular orbitals can accommodate 6 pi electrons. So if we have a cationic compound, then we're going to have an aromatic compound, because remember we had the 4n plus 2 rule. So we put 1 in here, this will equal 6. So triple ion cation is an aromatic cation. So, and this charge can move, as you can see right there. It says heteroatoms, atoms other than carbon or hydrogen, can also be part of an aromatic ring. It shows this p orbital right here. If a heteroatom's lone pair is necessary for aromaticity, it'll be included in the Huckel number of pi electrons. So here's the key word. If the heteroatom's lone pair is necessary, it will be included in the Huckel number of pi electrons. So like in this case right here, we have 2, 4, 6. This would satisfy the 4n plus 2 rule right here. So if the lone pair is necessary for aromaticity, then the lone pair will not be as basic. It says it's still aromatic, and here it's non-aromatic. That's because, we're at the 4n. We're not 4n plus 2. We can't get that with this right here. If we put a 0 here, we get 2. If we put a 1 in here, we get 6. And we have only 4 pi electrons. So it kind of does depend on the charge, because to give you an example right here, when this has a net positive charge right here, because nitrogen wants to be 5 minus 4, and that's how you get plus 1. Here, it's 1, 2, 3. So here nitrogen wants to be 5, and here it's 1, 2, 3, 4, 5. I'm counting formal charge. Here it's 0. So we have a formal charge of 0 right here. When we have a formal charge of 0, now we satisfy the 4n plus 2 rule. Well, actually, you don't satisfy it right here. You actually have to have you have to have this lone pair gone right here. So then here we have 6. This is a better example right here, where we have 1, 2, 3, 4, 5. So 5 minus 5. It's a neutral. It's neutral. These electrons are pointing up right here. They're participating. In here. So, there's how many pi electrons? Well, we count 2, 4, 6. That satisfies the 4n plus 2 rule. Here we're not satisfied, so the charge did make a difference right here. But here the lone pair, this is still an aromatic compound right here. But if you add this proton, because these lone pairs of electrons do not participate. So if the lone pair participates, it grabs this proton right here, it's still aromatic because you still have 6 pi electrons. There's 6 pi electrons here. It says if the lone pair is necessary. So here the lone pair is not necessary, is it? Because if we add them all up here, this would be 2, 4, 6, 8. we're not gonna be able to get there, because we'd be between 6 and that's if you put 2 in here. If you put 3 in here, 14. So actually, sorry about that. If you put 1 and 2, so this would be 6, and then 2 would be 10. Okay, so the question is, let me erase all this stuff. We're getting a lot of stuff on here. The question is, why is this one not aromatic? Why is this not aromatic? Well, it's aromatic in this case because, remember, if we just go by what this line says, it says if the lone pair is necessary. So if it is necessary, okay, so is it necessary to satisfy the 4m plus 2 right here? Let's just say we don't include the lone pair, right? We don't include it. And we have 2 pi electrons and we have 2 pi electrons here. That's a total of 4 pi electrons. Well, 4m plus 2, if I put a 1 in there, I get 6. If n equals 1, so you can put n equals 1, n equals 2. That's basically what we're working with, n equals 0. So 2, 6, 10. So we can't satisfy this because, we have to have a number that is 6, and here we only have 4. So the pi electrons are necessary for aromaticity. So if we put these 2 in here, now we get 6. So we get 6 right here. So if we look at this compound on the right-hand side, we're not able to get to 6 electrons because we only have 2 electrons here and 2 electrons here. Where are the other electrons? They're not there anymore because those other electrons took this proton right here. There was a proton transfer. So now we're only at 4 pi electrons. And, just according to the definition of being, non-aromatic, we are not. Let me see. So we have a fully conjugated ring with overlapping p orbitals. We don't have that anymore. See this right here? So that's the case right here. We don't have fully overlapping p orbitals anymore with that case where we had this here. So since we don't satisfy that, then we're non-aromatic right there. I guess we could have stopped at that point. These p orbitals don't overlap anymore. So I guess it goes back to the 4m plus 2. We don't satisfy the 4m plus 2, and we don't have the p orbitals overlapping because the p orbitals would be here. We may have to have a chat after class, which we can. The p orbitals may be here, and these orbitals, they're not sticking out the same way. I mean, to draw this nitrogen correctly, you'd have to, it's going up like this one's going down, and these ones are this one's going like that, and this one's coming out, right? So the orbitals are not overlapping right here. So we can talk more about that after class. It's just we only have so much time. Let's see. So the difference in electron density can also be observed by viewing the electrostatic potential maps. This lone pair is delocalized. This lone pair is localized. So it's delocalized. It's part of the aromaticity. And this lone pair doesn't participate right here. So to do this, they had to do some calculations to get these electrostatic maps. So they're both aromatic. It's just one lone pair participated while the other one didn't, and that comes back to this criteria right here. If the lone pair is necessary, the lone pair is necessary for aromaticity, then the lone pair will not be as basic. So if it was necessary, in this case, it is necessary. As many polycyclic compounds are also aromatic. We know that that satisfies it. And you can count, you know, the other ones here, 6. This would get me to 8, 10, 14. I put a 3. So we satisfy it there. The stabilization energy can be measured by comparing heats of hydrogenation. We can see how stable it is. So it says a carbon directly attached to a benzene ring is called a benzoic position. So we have 2 benzoic positions right here. It says recall that aromatic rings and alkyl groups are not easily oxidized. However, benzoic positions are readily oxidized by chromic acid. So remember, this is our benzoic position. If we go back to the definition of that, the carbon directly attached to a benzene ring is called a benzoic position. Here we're at our benzoic position, and we can be oxidized by chromic acid. It says the benzoic position needs to have at least 1 proton attached to undergo oxidation. So here there's no protons attached, right? Here there was 2 protons attached. So we have 2 protons. Here we have 0 protons. So there's going to be no reaction. The question is there a reason why it attacks that carbon maybe instead of the other carbons? These carbons in the ring would be more stable. So the question is, like, you know, maybe why doesn't it go after this one? I don't know, to be honest with you. You know, I'm just trying to think. Well, and it might be because there could be some stabilization with the charge here. You know, since it's close to the aromatic ring, you know, it could potentially help with stabilization right there. Here, that aromatic ring cannot help if it attacks here. There's no way this could help over here. So it's close over here, so it's more likely to help over here. So that would be my, you know, best guess at why it happens right here. And you got to have a proton because it has to be able to pull something off. Here it can't do that, and here, you know, it can't go right here, and it can't help it right there because it'd be pulling protons off right there. So that would be my best guess. It says permanganate can also be used as an oxidizing agent. Here we're at the benzoic position, and here we oxidize it. NBS could be a source of bromine, so benzoic positions are similar to allylic positions and readily undergo free radical bromination. But my best guess is that this has something to do with the stabilization of the charge. The resonance helps it out. So here we're adding a bromine to it. But it shows it had to have at least one hydrogen right there, right? What if this was a methyl group? Does benzoic bromides readily undergo SN1 substitution? So SN1 means it's stepwise. So first the bromine is going to come off, have a positive charge. So if it has a positive charge here, this stuff can be resonance stabilized then. It can stabilize that charge. That's really the reason why I think it's closest to the benzene ring. It says unhindered benzoic bromides undergo SN2. So if it's unhindered, right here there's some hindrance to it because there's some groups coming off. Here it's unhindered, so it can go in SN2, which is a concerted reaction. Here in E2 reaction B, this is, well, it's a concerted reaction. So E2 would be, this is coming off, this is going here, this is going to come off right here, all in one step. E1 would be, first we're going to protonate this, it's going to be a good leaving group, H2O, excellent leaving group, positive charge. Then we have elimination reaction. Base coming in here, taking that off, and then we'll have our double bond. So here's a summary of the reactions. If we have radical bromination, we can get the bromine group on there. We can put some oxidation reactions, get carboxylic acid. It can go either through SN1 or SN2 or SN1 or E1 or E1 or E2. They're just different tools now that you have. So under forceful conditions, benzene can be reduced to cyclohexane. So we're saying we're forcing this reaction. You can see this is a pretty high temperature right here, 100 atmospheres. And we're forcing it to go into cyclohexane. Says, however, alkenes can be selectively hydrogenated in the presence of a benzene ring. So here we're not really forcing the conditions. Look at this. This is room temperature RT. The pressure is not that high. It's just 1 atmosphere above normal, or I should say at 1 atmosphere is right at sea level. So we're just 2 atmospheres, and we can hydrogenate that double bond. So now this double bond here is saturated. But it's not touching anything inside. And the only way you know this, you have to experimentally to do this. So benzene can be reduced by the Birch reduction. Mechanism is similar to dissolving metal reduction of an alkyne. We get rid of one of the double bonds, and now we're not aromatic anymore, are we? So we have a nucleophilic attack at a single electron. is transferred. Then we have proton transfer from the methanol. Then we're going to transfer another electron to, once we're down here, sodium's going to transfer another electron. There'll be another electron transfer. So then you're going to have 2 electrons, and it's going to pull another proton from the methanol, and that's how you get the final compound. So I'm just going to leave it here because you may want to study the mechanism for a minute. And when you mean transfer twice, do you mean the electron or do you mean the proton? Okay, so it does proton. Okay, so yeah, yes, it does. So there's 2 proton transfers. And here's the second proton transfer right here. So this has to donate another electron, right? We get 2 electrons, and then there's a second proton transfer. So first, how we got there, though, we had the single electron transfer from sodium. They don't say. Usually sodium has, it's just not sodium metal in its own self. Usually it's with a cation, usually, it's with potassium or something like that. It says this mechanism was pretty difficult to understand mechanistically, with controversy lasting into the 1990s. I'm just looking this up. So anyways, there was a lot of debate going on about this mechanism. Yeah, so I thought about that myself. They don't say that there's 2 equivalents right here. So so whenever you do these reactions, if you really do these in the labs or in the lab, you really have to have your equivalents right. If you have one of this, you should have maybe 2 of this. Otherwise, I don't know how this is going to go on. But then it is in this ammonia solvent, though. So they do have ammonia as a solvent. So maybe you only need 1 equivalent of this due to the reaction conditions. And so this would be a separate thing to study on its own. So if you want further reading about this, what I would recommend is just look up Birch reduction in Google Scholar. pull up the mechanism for it, and then to read the paper. That's what I was starting to do. Because it doesn't say you need two equivalents. And they're really simplifying it right here. If you go look in the paper, they're really simplifying the mechanism. I don't know if we want to go all into that, to be honest with you, but they really simplified the mechanism on these diagrams, right? There's a lot more to it than this. They're just giving you the basic idea that there's an electron transfer from the sodium, then there's a proton transfer, followed by another electron transfer here, and then followed by another proton transfer, but there's more to it than that. It says, note that the Birch reduction does not completely reduce the benzene ring. The product has sp3 hybridized carbons on opposite ends of the ring. So now we have sp3 hybridized carbons on the end of these rings. It says the presence of electron donating alkyl side group provides regioselectivity. So this is not reduced. So this is not observed. So if you have this right here, if you have some type of alkyl group, because remember in this we just had benzene, right? If we add just, I guess if it just add one, which would be toluene, this is not going to be reduced and this is not going to be observed. It says an electron donating group destabilizes the radical cation because it's donated electrons, and so reduction does not occur at a carbon possessing electron donating group. And the only way to know that is to experimentally go ahead in a lab and do that. So the presence of electron withdrawing group, so oxygen is electron withdrawing group, results in the opposite regioselectivity. So this is not observed. But this is reduced right here. Let me see something. slide 50. So I have 2 electrons right here then. I'm going to pull a proton from the ethanol. And then this will donate another proton or electron here. And now we're going to pull another one again from, I'm just following what they showed before. That's kind of my best guess on how this would happen. But there is an electron donating group that kind of messes with it, because then the electron density, so this electron withdrawing group right here, so it's going to pull this electron density. It's not going to push electron density into that. So we don't have to worry about that. Now with electron donating groups, you have to worry about the electrons being pushed in there. And so we're not going to have the opportunity for this sodium to donate its electron right there. So that's kind of my observation with that. These are really good questions and thought-provoking questions. So characteristic signals in the IR spectrum of aromatic compounds. I forgot, we talked about this in one of our chapters already about IR spectra, so we'll just have to refer back to that chapter. It says IR spectrum of ethyl benzene. You just kind of have to look for the characteristics stretching, and you find this, there's tables for this stuff up here. I don't have this stuff memorized. Sometimes it generally, I'll know where the OH peak comes at, but I will go to the table to find, where these peaks come at. Here's an NMR spectra. When we talked about in the NMR section, these are where the protons show up when they're on the benzene ring. And here's your allylic protons right here. So this one, it sees this one and it sees this one. So that's why it's a triplet, right? You have 3 protons. This one's a quartet because this one sees this one, sees that one, and it sees that one. So you have n plus 1, so it'd be 3 plus 1. You get a quartet right here. This is a multiplet right here. We have 2 protons, and we have 5 protons. So you have your NMR and you have your IR, and all this does is help you put together the structure. So the integration and splitting of protons in the aromatic region of the proton NMR is useful for rings with multiple substituents. Here they're the same substituent, so we have a mirror plane. And we see that we have only 1 singlet. Here we have 2 doublets because this substituent is different right here. So they're going to be, the hydrogens are going to see each other differently. says in carbon 13 NMR, so this is not proton NMR, the carbon 13, which carbon 13 has how many protons? 6 protons and 7 neutrons. Carbon 13 NMR carbon atoms of benzene typically appear from approximately 100 to 150. So you have two different signals right here. What they should do is just label the carbons like A and B. You know, I just label this one to A and these ones to B. Here you have 6 different carbon signals showing up. Here you have 3 different ones. That would be 4. So if they would have labeled it A through D, I think that would make it a little better to understand. It says graphite's a form of carbon, just like diamond's a form of carbon. So graphite consists of layers of sheets of fused aromatic rings, just like buckyball fullerenes. I met the guy. There was 3 people that invented this. Who did I meet? I met Robert Curl. They won the Nobel Prize in Chemistry for this. It was Kroto, Curl, and Smalley. It says fullerenes can be made into tubes. So this was a big thing right here, carbon nanotubes. So, you know, I mean, this was a big deal at the time because they were thinking about doing all this nice, neat things with this because this would be so strong. You know, they were trying to make, there was talk about space elevators and other things, you know, just all types of different applications. But the problem is, you know, to make them long, you know, how are you going to get and enough material? And this is really expensive too to make. So there's lots of different problems with this, but the use of fluorometry to measure, you know, absorption and emission spectra with it. They also use UV visible spectrometry too, and we talked about that, you know, as far as like conjugation. So those were some techniques that they're used to measure these carbon nanotubes. So that's it. We'll go on to the homework. Let's take a break. I'm going to make the homework up while we take our break. So let's come back at 11 o'clock. And I don't know how many questions we're going to get through, but whatever we get through, that'll be it for the homework for chapter 17. And then we will go on to, then we'll have chapters 12 through 17 on the exam. So, you know, if we only get through a few questions, that's okay. However many we get through will be the number of questions for this homework. So I'm going to stop. We'll take our break, and then we will reconvene. All right, everyone, welcome back. We will go on with our chapter 17 homework now. As always, we'll start with question 1. And like I said, whatever we don't finish today, we won't have on the, you know, we won't, it'll just be what it is, but it's fine. It says for each structure, provide the common name. So we have A through D. Oh. This one is toluene. This one is benzoic acid. This one is phenol. This one is aniline. You gotta have to look for the group. This has a nitrogen, this has an OH. This will have this, and toluene will just have a methyl group. So you gotta kind of look for the group that you're looking for, the functional group. So that should be for question 1. We can do question 2 on the same slide. It's just another naming. Question 2 says, now we have this. What is that called? That's just ethylbenzene. That capitalized. And there's a part 2 to it. This will be chlorobenzene. We have our 2 names. That's questions 1 through 2 done. All right, we'll go to question 3. Question 3, it's another naming. We have this. And they want to know what that's called. That's called 1,3-diethylbenzene. And then I have this one. So if you have something different, you gotta kind of pay attention to where your substituents are at. This is 1,4-dichlorobenzene for me. And I'm going to draw 4 on the same one. It's kind of similar. No, that would be fine. Just see what it does though. It should be okay. If it doesn't give you, just put 1,4-dichlorobenzene, but it's the same thing, you know, because this would be the ortho, meta, and para position. So we have that, and then we're working on 4. 4 gives you all the different options. Here it could be 1-bromo-3-ethylbenzene. And then the other 2 options are meta bromoethylbenzene just select the ones with meta. Actually, this will be easier. And then M is meta too. So select this one, and select this one. So did it give you it correct when you put para-dichlorobenzene? So just make sure that make sure all the spelling's correct. It should work. Okay, so that works. So that's good. So we have quite a bit of them done. Let's go to 5 then. Oh, somewhere it's not ready. 5 has this. So it's going to go alphabetical. So we have 4 bromo. Remember, this is kind of like, you know, kind of our parent. So this is going to be a phenol. So it'll be 4 bromo, 4 bromo, 2 chloro, phenol. We can do 6 on the same one. A lot of naming going on. So this is kind of like your parent right here. That's a toluene. So ortho meta para. So at the para position, you have a propyl group. So propyl toluene. So 7 gives us this right here. All right, so if you start up here at 1, 2, 3, 4, 5, this is 3 methyl. The 3 position of a methyl group, 3 phenyl pentane. Eight is something they want you to draw. It says draw 4 ethyl phenol. So we draw a phenol group. They want you to put the double bonds in. Put the OH here, and we'll put the ethyl group there. So that's what they wanted. All right, we'll go to 9. There's a lot of naming. I think we're going to get rid of 9. Um, I think we've done a lot of naming so far, so we're going to get rid of 9. 9 will be the frost circle now. Let's consider the structure of cyclopentadiene anion. So that's what they're saying. To complete the frost circle. So how many pi electrons? 2, 4, 6. I should have. There we go. And this is aromatic. Ten. They want you to say how many pi electrons there are. So I have 6 pi electrons in mine. Compound A is aromatic. B, I have 10 pi electrons. And we know from 4n plus 2, this was going to be aromatic too. So this right here, I'm not the best drawer. This right here is just like an alkyl group coming off, you know. So just ignore this. This is just another alkyl group. This is just some type of carbon group coming off. So what's important is that's aromatic right there. And let's just say we had, you know, this right here, you know, you wouldn't have even considered it. So this is an aromatic compound. So let's go to 11. It says compound A. So how many pi electrons are in compound A? 6. So that's aromatic. Compound B, 2, 4, 6, 8, 10. And this is also aromatic. If any time you forget, you know, you have your 4n plus 2. You mean for compound A? So for this one right here, two, 4, and then this one right here is the one that's going to be added to it. This one right here, that's going to be off in the distance. Remember, we can add these lone pairs of electrons if they will make it aromatic. So that was the whole key statement from that one part we read in chapter 17. So if we add these 2 electrons right here, we'd have 8 and would make it non-aromatic, right? Because this is, you know. So if it can make it aromatic, we'll add it in there. So since these 2 electrons would not add to the, it doesn't make it aromatic, they're going to be left out. Yeah, so once we find that it's aromatic, we're going to stop adding these 1 electrons. But, you know, I don't want to say that because let's just say you had, I don't know, just trying to make something up here. Something like this. So, I mean, you can't just stop right here and say, oh, I have 6 electrons. We're only saying that for lone pairs of electrons. So now let's go to compound C. Compound C is this right here. only have 4 electrons. This is going to pucker up like this. And then you have to go back to line 1. And what do I mean by line 1? Let me. So line 1, if you go back to the criteria for aromaticity, line 1 says a fully conjugated ring with overlapping p orbitals. This doesn't have overlapping p orbitals if this is puckered up like that. So that's going to be non-aromatic. Compound D, it has 6, so this is going to be aromatic. Compound E has 2, 4, 6. This is also aromatic. You know, this would be sp3, sp2, 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 sp2. I'm not the best drawer at these things. Here we have all sp2 high carbons, right? Everything's sp2. I mean, we could keep on going. It's all going to be sp2. So if 2, 4, 6, 8, this is going to be anti-aromatic. So what I mean by that is if I can let's not think about it like that. Let's think about the hybridization of the carbon right here. We have an sp3 carbon right here. And that sp3 carbon is going to have, you know, a hydrogen coming out right here and a hydrogen coming out right here. Like I said, I'm not the best drawer of this stuff, so it'd almost be nice if I could turn it like this. But see, they're not in the same plane now. You know, so they're not overlapping, but in this case they are overlapping, and that's why this one's going to be anti-aromatic. So now we get to talk about in question 12 aromaticity and delocalization. So let's look at A. So A, we have, it is an aromatic compound. And is that lone pair delocalized? That means is if localized would mean, or delocalized means it's participating in the with the aromaticity. So is those lone pair of electrons participating? No, they're not, so it's not delocalized. I'm just going to put not. It's easier for me. So this one we have 6 pi electrons, that's aromatic, and they are delocalized. C, 2, 4, 6, we have an aromatic compound, and the lone pair of electrons are not delocalized. D, we have, again, this is the aromatic compound, and we have one lone pair that is delocalized. That lone pair participates in the aromaticity, so it is delocalized. We can also do 13 on the same slide. It says 13 says, indicate whether or not each of the structures is aromatic. So we have structures A and B. Okay. So structure A is not, and this is. So A is not because I like my best effort right there. So this one is going to be sp3 hybridized, where these carbons are sp2. So that comes back to that one line. A fully conjugated ring with overlapping p orbitals, it's not going to have overlapping p orbitals. And that's because the nitrogen is tetrahedral and sp3 hybridized. That nitrogen does have 4 things bonded to it, has 2 carbons and 2 hydrogens, it's tetrahedral, and it doesn't fulfill that line that says a fully conjugated ring with overlapping p orbitals. It doesn't have overlapping p orbitals. So let's go on to 14 then. Well, with sp2, if they're all sp2, then they're all going to be overlapping with each other. And that's why I like to give that case a cyclotetraocta triene, or this one right here, where these are all sp2 hybridized carbons. They are all overlapping, but it's not aromatic, it's anti-aromatic. No, they're all overlapping with each other, right? But it doesn't fulfill Huckel's rule. So it's because the nitrogen is sp3 hybridized. That's correct. So let's go on to, let me see, where are we going on to now? We're going on to 14. 14, kind of the same thing. We have an A and B, 2, 4, 6. They're both aromatic. So you're going to select aromatic for both of them. And the first one, I don't want to, it's kind of like this, right? Well, these electrons can jump right there. Then if it jumps right here, the positive becomes here, and they can just keep on jumping. And with the second one, you have the nitrogen. These are sp2 hybridized, okay? And these electrons participate. So then you have 6 electrons right there. And we can do 15 on the same one. 2, 4, 6. So B is aromatic and A is not. So that's 15. 16 we could do on the same one, and that's just a common name. That's called pyrrole. So so the question, could you say the good tip to see? So yeah, the good tip is to see whether sp2 or sp3 hybridized. But then, then we have to figure out if they're all sp2, then they have to be either, if it's in a cyclic ring, then they'd either be aromatic or they'd be anti-aromatic. But if they have sp3 hybridized hybridization, well then it's going to be a non-aromatic if it's within the cyclic ring. Let's go on to 17. Moving along pretty good. You just have to identify the benzylic carbons. Remember, the benzylic carbons are just one from the and you should be able to do this on your own. If you have this, well, this would be a benzylic carbon, right? Or this would be a so if you have a bunch of this, well, this is the only one. So you're picking the carbon right next to the benzene ring. That's all you're doing. So that's 17. And compound A has 4, and compound B has 2. So if you don't select 4 and 4 carbons, you're not selecting all the benzylic carbons for compound A. And compound B has 2 benzylic carbons. Compound, or not compound. Question 18. Remember, we have this. We have some hydrogens here. We're adding an oxidizing agent, KMnO4. That's potassium permanganate. And what do you think we're going to get? Oh. So sorry, they wanted this structure right here. So we already kind of already drew the answer. So that's okay. Now here's a good one. For question 19, they give you something similar, and they want us to draw it. Well, at all benzylic carbons, we're going to draw carboxyl groups. So let's do that. So at every single benzylic carbon, we drew a carboxyl group. You can see these problems are really not that difficult. In question 20, question 20 is just like 19. Oh, I'm trying to draw it so quick because it's all the same thing. So it just transforms that alkyl group into a carboxyl group at that benzylic spot. 21 wants stability. So they say label the carbocation that is the most stable. And this will be the last question we have. So the most stable one will be the tertiary carbocation. And then we have the least stable one will just be the primary carbocation. And this one has some resonance stability to it. So those are your answers right here. So most stable, most, and then this will be the least. So that should be 21. Like I said, we'll end right here. I'll take any questions. Now I'm going to stop the video.